In this video, we're going to be covering enzymes. So let's first start off with enzymes and activation energy. So the core idea is that all chemical reactions, they require activation energy, which is EA. This is activation energy. And activation energy is the energy needed to reach transition state. What does this mean? Well, it means that all reactions need this, and this means that even spontaneous reactions need EA. And if you're wondering what spontaneous means, spontaneous is when your delta G is less than 0, so it's when delta G is negative. So think about when you are pushing a ball uphill before it can roll downhill. So what are the functions of enzymes? Enzymes, they lower the activation energy, so it's easier to do something. But what they don't do is they do not change your delta G, your equilibrium position, nor whether the reaction is spontaneous. So enzymes speed up the reactions by lowering the activation energy without changing delta G or the equilibrium. So another thing that you have to know about is Gibbs free energy. This is represented by delta G. So what delta G is it's equal to the products G minus the G reactants. Now, there are certain values of delta G that you have to know. So when delta G is negative, this is when you have a spontaneous / exergonic reaction. When you have a delta G that is positive, that means you have a non-spontaneous or endergonic reaction. And you have a delta G that's equal to 0. This means you are at equilibrium. Remember that spontaneous does not equal to fast. And also, remember that a reaction can be spontaneous but slow without an enzyme. Now, let's talk about enzyme denaturation and cofactors. So, enzyme denaturation is when the enzyme loses its 3D shape. And this is when one of three things happens. So the first thing is the temperature is too high or it's too low. Secondly, this happens when the pH is out of your optimal range. And thirdly, this happens when you are exposing your enzyme to certain chemicals that are unfit. So once it's denatured, it stops working. You don't want that to happen. And some cofactors. Cofactors, essentially, they're just helper molecules. And they help the enzyme to function. So some examples of these are vitamins, vitamin-like molecules, and also metal ions, which includes Zn2+, and also Fe2+. And if an enzyme doesn't have a cofactor, the enzyme is inactive. Now, let's talk about enzyme inhibition. So, essentially what happens is there are molecules that bind to the enzyme in some form, and they inhibit the function. But they can dissociate. These binding molecules, they can dissociate. So there are different types. Let's first talk about what happens normally. So we know that normally, that when you have an enzyme, you have say this is our enzyme, and then we have this. So we have our substrate, and we also have our active site, which is the location that it binds to the enzyme, and then this is our enzyme. So this is what happens when you have normal binding. But let's say that something changes. If something changes, we have our first scenario is competitive inhibition. And what this means is that you have a competitive inhibitor. So you still have your substrate, but now there is something that's blocking it from binding it. That is your competitive. It's a blocker at the active site. Now, if you have non-competitive inhibition, it means that something is sticking to it, but it's just not in the place that is necessarily important. It's not important to the active site. And the site that it bonds to is called the allosteric site instead of the active site. Now for uncompetitive inhibition, it's similar to non-competitive inhibition, has a similar name. Except it's just a little bit different. So at this point, the substrate and the enzyme have already bonded, but now there is a uncompetitive inhibitor that sticks on the outside. It's basically too late though, because the substrate enzyme key lock model has already binded together. So some things that you have to know about these for competitive inhibition, just think it's like competing for the active site. So it mimics the substrate. Now for non-competitive inhibition, it binds to E and ES equally. But something else that you have to know is that allosteric inhibitors, they bind to the site other than the active site on enzyme to disable it. So basically it finds a second point of vulnerability and then it targets that place and then it stops the enzyme from functioning. So now uncompetitive inhibition, it binds to the ES complex only, not any sites. Now we can talk about allosteric regulation. This has two L's. So what happens is that we have allosteric activators and inhibitors. What does this mean? Well, we can imagine something like this. We have this complex. This is in its active form. So it has an active. So this is one of 4 active sites. And this is an allosteric enzyme. This is a regulatory site. Which is one of the 4. There's one on all the other side parts too. And then what happens is it goes from this active form to a stabilized active form. What happens is that you have these substrates coming in, and you also have a different item that is coming to bond. This is called the allosteric activator. And what it does is it stabilizes the active form. So then after that we can color code these. There's also, from this form, it can go back and forth and oscillate to an inactive form. This is when it's like deformed. And then it cannot be activated. It's inactive. And from this inactive form, it can transform into a different form. So in this process of being transferred, we can actually write so there's going to be this activator. And then this is going to be our inhibitor. So your allosteric inhibitor, what it does is it stabilizes your inactive form. And basically it's inactive because every single time one of the substrates tries to bond, it just is bounced off. So unsuccessful bonding. So this is our first type. Moving on to our second type, we have allosteric regulation. Which is when you have allosteric regulation activation, which is called cooperativity. So in our inactive form, we have and then in comes our substrate. And then our substrate, it bonds. So basically, if you bind into just one of the subunits, it makes the rest of them bind, they lock into their correct active conformation. So now it's in its stabilized active form again. So it can be bonded to with other substrates. So this can actually oscillate with the active form when the active form is not stabilized by the substrate. Now, what we should discuss next is Michaelis-Menten kinetics. So what this is how the reaction rate depends on substrate concentration. So key variables that you have to know are Vmax is equal to the max reaction rate. S is equal to the substrate concentration. Km is equal to the substrate concentration at 1/2 of Vmax. So to interpret Km, low Km means high enzyme substrate affinity, and a high Km is going to be equal to a low affinity. So this curve, what this curve looks like is that we have something like this. It's split into a fast portion and a slow portion. And then this is measured in velocity, meters per second. And this is going to be, you're going to have a line here and a line here. So we're going to draw our curve. And this is going to be low concentration and high concentration. So this is your substrate concentration measured in M. And this is your reaction rate. So this specific point, we'll call that Km in M. And these other points, these are experimental. Data points. This is a mathematical model. So we can see that the curve plateaus at Vmax. And Km is going to be at the point where the rate is equal to 1/2 of Vmax. Now, this is also known as V, your y-axis is V. This is also known as V initial. And Km, again, is the point S substrate concentration when the reaction rate is equal to 1/2 of Vmax. And we can also use not just the Michaelis-Menten kinematics model. We can also use the Line-Weaver-Burke or double reciprocal plots. Now this is going to be the graph into a straight line and some important features that we're going to draw. It turns the MM. So what we have is our graph. And we have our line. I'll make this red as well. And our slope is going to be equal to Km over V, and our intercept point, this is going to be at 1 over V, so your axis is 1 over V, and then this point is going to be 1 over Km negative. And you're going to have all your points, they're kind of just like loosely scattered with this line of best fit. This is going to be 1 over A. But actually we want to draw these getting kind of further apart. Because the dispersion is greater at 1 over A. So this 1 over V, that's V max. Also call that initial. This is negative 1K over M. This axis is 1 over the substrate concentration. That's max. And what you should know is that 1 over Km, that is your X int. And your Y int is going to be 1 over the Vmax. So you really need to know when the intercept changes. That's really important. Now, going back to competitive inhibition, I want to add a few things. So, again, remember that it mimics the substrate and it binds to the active site. But it can be overcome by an increase in the substrate concentration. And the effects of this are that Km is increased, but your Vmax is the same. Now on the Lin-Weaver-Burke model, you have the same Y int, but your X int shifts and your slope will decrease. Well, actually, I want to move some of this down. So, for non-competitive inhibition, it binds to E and your ES. and it's usually allosteric. Now the effects of this that I want to discuss are that on the Michaelis-Menten graph and the Lineweaver-Burke, Weaver-Burke, so the effects are Vmax, it goes down, and your Km is going to be the same. Now on your Lineweaver-Burke, it's going to be the same x int, but this time your y int, it decreases, and your slope changes. So uncompetitive inhibition, this is when it binds to the enzyme and the ES. It's usually allosteric, and it cannot be overcome by an increase in the substrate concentration because it would just bind anyways. Now, let's talk about the effects on uncompetitive inhibition. Oh, this is for non-competitive. Actually, this is for this. So what happens in uncompetitive inhibition is that your Vmax is decreased, your Km is going to be the same, just like all the other ones. You're going to have the same x int, your y int is going to increase, and your slope will change. Actually, no, your x int is going to change, your y int is going to change, and then your slope is the same because the x and the y int will change at the same amount. So in total, remember, competitive inhibition is the active site. Non-competitive inhibition is going to be the E and the ES. Uncompetitive is the ES only. We can see here Km is increasing. We can see that here in non-competitive. In non-competitive, Km is going to be the same. And then we can see that in Michaelis-Menten, your Kmax is going to be decreasing. So now we can look at the Vmaxes. Well, your Vmax is going to be the same, and then that's for competitive. For non-competitive, your Vmax is going to decrease, and then for your uncompetitive, your Vmax is going to decrease. So remember, if the question is asking adding more substrate does not help, when adding more substrate does not help, that is going to be non-competitive.